Okay, good morning. The seminar of today will be presented by Frank Schinzel from National Radio Astronomy Observatory in New Mexico in USA. He will talk about the Very Large Array scar survey and the next generation Very Large Array. Frank, he made his PhD in Germany at the Max Planck Institute in Bonn about the AGN relativistic jets, and then he moved to New Mexico in Albuquerque to make 5-year postdoc about the low radio frequency instruments. Now he's a staff scientist at Socorro, and he's doing mainly telescope support at the VLBA. Frank, thank you.
Thank you, and thank you for coming and listening to me. It's a pleasure. It's the first time for me in Granada, and I thought I'm here on vacation, and I thought it's a good opportunity to also stop by here and give you a kind of an update of what we've been doing in the US and community. And I don't know how much you've heard about the VLA Sky Survey so far, or the next generation VLA. There have been quite a few talks around in the SKA arena, but so we thought that this might be a good opportunity to update everyone on where we are. And just to say something about myself, so I'm doing VLA and VLBA telescope support as well as user support, and I'm involved in overseeing mainly the low frequency system on the VLA. So we have a low frequency system that can observe at 74 megahertz and 350 megahertz. And so I'm overseeing the scientific side of that. And the other part is I'm heavily involved in the VLA Sky Survey itself, in the development and verification that the data quality is up to the requirements and the specifications, and in particular the polarization aspects of it, which is something I'm only going to touch a little bit on. So I don't know if everyone is familiar with the Very Large Array. So here's a little bit of a history of the Very Large Array. So this is a picture of the core of the array when it is in the most compact configuration. It was basically approved in 1972 by the US Congress, and then 75 to 80 was basically the construction phase, and then it transitioned into the full science operations. And then the narrowband and the new digital electronics came along, and it was basically upgraded in the beginning of, or at the end of the 90s, the beginning of the 2000, and that was completed in 2001. And then it took about 10 years to commission that new new mode, full digital with 8 gigahertz of bandwidth for the whole array. And so this is how we have been coasting along since then. Just something about the location. And so it's in the plains of San Agustin. So we're in New Mexico in the United States. So we're still in the United States, but close to Mexico. If you know where Albuquerque is, there's Albuquerque, and the VLA is down here. And that's a scale, 50-kilometer scale here. And so there's a Y-shape tracks. So these are actually railroad tracks, and we can move these antennas around on those railroad tracks so that we can reconfigure it into different configurations. And yeah, just to say, and this gives us distances between the antennas from a minimum of 35 meters to a maximum of 36.4 kilometers. And then we have 10 operational bands from about 50 megahertz to 45 gigahertz. And that gives us resolutions with the reconfiguration of 850 arc seconds to 0.043 arc seconds. So this was just the overview of the VLA. Now coming to radio surveys. So this is kind of a history of radio surveys, and in terms of how many sources were in those catalogs and the date when they were published. And at the beginning of radio astronomy, there were of course only single dish telescopes, and so there were only a few sources that were detected due to the confusion limit. And then the interferometers came along, and then this started, and then it's kind of flattened out in terms of sources number count. And only in the recent years, well, with NVSS, with the exception around this time, in the recent years we see this kind of change in number of sources in catalog. So we have the new EMU survey and the LOFAR surveys, Aperitif, and now also with the VLA Sky survey, we're expecting to see an increased number of sources, mainly due to either opening some new parameter space that has not been opened before. So what is the Very Large Array Sky survey? It's the highest spatial resolution all-sky radio survey to date that we're undertaking. We're trying to do, so we're doing all sky that is observable from the VLA, which is from minus 40 declination to plus 90. It is at a frequency, the center frequency is 3 gigahertz, but we're actually observing 2 to 4 gigahertz. We have a little bit of RFI that we're dealing with, that we have to flag and lose a little bit of bandwidth. You're getting also the full spectral resolution that we can easily handle, and that's the 64 times 2 megahertz channels per spectral window, and then we have 16 spectral windows across that whole bandwidth. And we are observing this in a B and B North A configuration. What that means is that the B North A is mainly meant for lower declinations, and in order to keep a synthesized beam shape that is more or less circular, we're actually doing this hybrid approach where we use one VLA configuration and then we use the northern part of the array in a more extended configuration to keep the beam shape circular when we observe at low declinations. And then another feature of this survey is that we have 3 epochs that we separate between, by 32 months. So that way we get actually a time series, or you get 3 points in time of the whole sky. So you can actually see. So I will go into that, why we're actually doing that. And we're also doing full polarization. And the total observing time, 920 hours per configuration cycle. So times 6, that's about 13% of the VLA science time, and 5,500 hours. And the duration is September 2017 we started, and we're hopefully going to finish in October 2024. And yeah, these are the key parameters again down here. So this is just an illustration of the sky coverage that we get, and so we're basically observing this in the B configuration, or what we call the B configuration, and then the lower declination. We have a little bit of a transition region where we can get away with either configuration, and then those we're doing in B North A. And if you're familiar with the VLA observing cycle, so we have a B array, and then we have regular PI signs running during B array, so this is dynamically scheduled. Within that, in about each chunks of 4 hours or 6 hours, and then once we're going into this special B North A configuration, then we have then we're exclusively observing for about 2 weeks the sky survey. So that's the setup. One new feature that was enabled also with the upgrade of the VLA is we have now something that's called on-the-fly mosaicing. So in the past, the old NRAO VLA Sky survey was done with pointed observations, and then those pointed, so you do single pointings, and then you combine them into a mosaic. What we're doing this time around, in order to save time, the settle time of the telescope, we actually go and continuously slew with the telescope and record data. And we're doing this for about 10 degrees, and then we go around, and then we go another 10 degrees in this direction, and then we keep stacking up across the sky. This is very challenging for the telescope because it's pushing a lot of the limits. We have to have this fast dump correlator backend, so we have to dump at 0.45 seconds each visibility. But at the end of the day, we're getting 20 square degree per hour as a survey speed. And that's our scan rate. How fast we're scanning is 3.31 arc minutes per second. And that's the correlator dump. And so we're saving basically 2 integrations per phase center we're updating. So we're stepping through here with phase centers, and then that way record. And then in addition to that, we had to develop a pipeline that can actually reduce that data or calibrate the data and produce the images in an automated fashion.
Excuse me, the sensitivity number you gave in the previous slide, that was 120 microjanskys per epoch, is based on these 5 seconds?
Yes, exactly, yeah.
Okay. Thank you.
And that you get because of the wide bandwidth, because you have 2 gigahertz of bandwidth. So the survey, what it produces is, so NRAO has committed to generating basic data products. And those basic data products are defined as the raw visibility data, which is available immediately, and you can download from the NRAO archive right after the observation. Then we calibrate the data, we run it through the pipeline, it runs through a quality assurance, so data analysts look at the results from the pipeline and verify that everything is consistent, and then once they accept it, it will be, those calibration tables are accessible from the NRAO archive, and this is all done in CASA, if you care for the software package. And then once it's accepted for the calibrated data, then it automatically launches the quick look imaging. So there's a separate pipeline that then gets launched, and it produces 1 square degree images, quick look images, and we have a nominal 2-week turnaround. We're actually meeting that for about 80% of the sky, and then there's 20% of the sky where we need to put some additional work in, additional RFI flagging in order to produce those images. However, the issue with the quick look images is these are supposed to be quick. So we're trying to be as quick as possible to produce those images so that transient people, they can actually look at the images very quickly after observation. What we would like to, what we produce for the actual science are the single epoch images and the single epoch catalogs. And those are the Stokes I wideband continuum, similar to the quick look, but with higher resolution. We're also going to produce Stokes I Q and U cubes for polarimetry, and then a catalog that comes with the single epoch images with all the sources that were found in that particular square degree. And then once we have more than one epoch, we basically add those together in order to get the higher sensitivity. In addition to what we are providing from NRAO, there's also a community producing enhanced data products, and the most notable is CERADA, which is the Canadian Foundation for Innovation, has funded this project which is larger than just VLA Sky Survey. But one aspect of that CERADA project is to produce cross-matched multi-wavelength catalogs, all sky cubes for rotation measure analysis, and transient alerts from VLASS, which I will mention in the next slide, and multi-epoch data. So this is this is basically generally the entire data volume is about 1 petabyte that we're going to store. But not stopping there. There's also some serendipity built into VLASS. There's a system called VLIGHT on the VLA, which can record whatever the VLA is doing at 350 megahertz, and that's being run by the Naval Research Lab. Currently, they can record with 15 antennas simultaneously, and they get, I'm trying to remember, I think it's 128 megahertz bandwidth. And so they observe parallel with VLASS, and we're getting basically another sky survey for free at 350 megahertz, which is called VCSS. And here you just see a comparison of NVSS at 1 gigahertz to the 350 megahertz VCSS, and then the VLASS image. At the same time, we also have RealFast. RealFast is a separate backend that funnels the data out of the correlator before it gets averaged, and it basically looks for fast radio bursts. So while we're scanning the whole sky, we're also looking for fast radio bursts with RealFast. That system, unfortunately, is not yet quite functional, but it's very close, and it's currently under development. But we'll get there hopefully by the end of this VLASS observing cycle. So certainly by VLASS Epoch 2, both of these systems will be fully operational. So where does VLASS stand in comparison to other surveys, older ones and newer ones? And you can see that VLASS is in some sense unique in terms of where it is in the frequency spectrum. So this is frequency versus the sensitivity. So it's pushing a little bit. There is no all-sky survey in that range so far. So we're pushing the limit, and also in resolution, it's the highest resolution survey, so you can't even see the resolution circle here on VLASS. And this will fit very nicely with the SKA Pathfinder surveys, or also the lower frequency surveys, LOFAR and high band antennas. So this will become a very nice asset to combine with other surveys that are currently released and are in the making. So not everything is great. When you're trying to do a survey, you're actually testing your instrument heavily, and you find new things. So you have to do quite a bit of design and development work in order to make this work and reliably. And so one thing is the goal is sensitivity required to do better than the previous L-band surveys, and especially when we're also producing spectral indices. And so there was a lot of work that had to be committed to getting this whole on-the-fly mosaicing working for the Sky survey, and we spent a lot of time figuring that out. And there's still a few issues that are remaining, but I think we're mostly through that. The other part that we have to constantly keep an eye out on is S-band RFI. We don't have any real protected part of the spectrum between the 2 to 4 gigahertz, and there are a lot of satellites, especially there's a geostationary satellite constellation that is providing radio over the US, and that is always there. And so when your source gets close to those satellites, then you get your compression in the receivers, and your data can become useless. So in order to first recognize it, and then second to correct for it, we have developed, so that what we have in the VLA system is we have a so-called switched power system, where we have a noise diode where we're switching back into the system, so that way we know whether we're going into compression, and we can actually estimate the compression based on that, or the nonlinearity of the receivers. And so we have a measure of when we're getting compressed. So what we can do is we can generate templates in order to compensate for the compression. And then in some cases you cannot avoid it, but you have to flag. And so we have some flagging heuristics developed specifically for VLASS to get rid of the stuff that we can't just correct for. And sometimes RFI is just there. I mean, even if you have compression, you will always have RFI there. But you might be able to save more bandwidth. To give you a visual representation of where the RFI sits in the sky, so this is declination in degrees. This is -5 declination, and this is -2.5 going to 0, +2.5, and so on. And so at -5 declination, that's about where the geosynchronous satellites sit. But you can see that they're actually floating around, and so there's a part in the hour angle versus declination where the red part is we really want to avoid observing there. So that makes the scheduling a little bit challenging, especially if you want to keep your synthesized beam circular. So science goals. So of course, by doing an all-sky survey, you want to provide a reference of the radio sky, and we want to do this at a high angular resolution, and in order to do multi-wavelength studies on those objects. So one of the main goals is to image galaxies, reveal the hidden explosions. So that means since we have 3 epochs, we can actually go in and see, has something popped up from one epoch to another, and is there a slow transient that we would have missed otherwise? And there are a bunch of cases where we have GRBs or supernovae that were missed by conventional means of searches. One of the real big new things, in my opinion, is the Faraday tomography has been done in the past using NVSS, but NVSS was not really designed to do very well with polarimetry, so we're going to try to do this much better, and then that way, this is basically the first full polarimetric all-sky survey that we can do this with that kind of bandwidth. And then, of course, there's also being able to look through the galactic plane and some missing stuff. And you never know what you find in an all-sky survey. Just some recent examples of what has been already done using just the quick look image products, which were never really meant to be the final data product. Here it was intended for something like this, where a potential orphan GRB was detected, and VLASS provided some data for that. There's the giant radio galaxies. It makes it much easier now to identify giant radio galaxies and actually to cross-match them with the optical side of things. So that Heinz Andernach and his students are usually or they're very keen on doing this, and they've been looking through those images. And then, of course, polarization science. This is just from verification work where we used some NVSS rotation measure maps and verified with VLASS that we're getting roughly the same answer, just to make sure that everything is consistent. And this is just to demonstrate what you can learn. It's a little bit hard to see here. So this is an SDSS image here, and then you see here some green contours which are from the first survey, which has roughly the same resolution as VLASS, but actually VLASS is a little bit better, which is the blue here, and you can identify this galaxy with this blue outflow. So, and this is from pilot data. So we did actually, before we actually started the full all-sky survey, we did a small part of the sky as a pilot a year before in order to test a lot of the algorithms and tools that we developed. We're also producing HIPS images where you can scroll around and on the sky, and you can look at your favorite part of the sky. Those are available, and then, of course, as I pointed out, is that for radio galaxies or for morphologies, we can now, it's much easier to determine the morphology of sources that are detected with the higher resolution. So VLASS 1.1 we observed. We started September 7, 2017, and we finished February 20th, 2018. We had heavy, lots of wind, so we lost a little bit less than 1%. Due to those high winds. And we have completed all of those quick look images. They're all available, and less than 1% were rejected because of quality issues. This gives you an impression of the source count distribution. So this is running just a source finder over all the images. And we found, this was a student of mine that did this as a summer project, and he found 1.3 million sources. And so we're extrapolating that for the VLA sky, we're expecting about 2.6 million sources, and which translates to 3 million for the whole sky in that band. And you can see where the sensitivity limit drops off. Just one thing to point out, this gets a little choppy up here because we have issues with bright sources. We have to sometimes, they're getting flagged the areas in the sky around bright sources, and you can see that even more clearly here. So this is the sky map of the first half of the VLASS observations, and these are all the sources. So this is not an image. These are the actual sources that the source finder found, and you see these spots here, and this is probably where a bright source is sitting, or here there might be some RFI issue when this data, or wind, when this data was taken. There's also another project that's been going on led by Shia Brown, and they are experimenting with machine learning, and they're training their algorithm based on the VLASS quick look images, and so they can produce basic catalogs and postage stamp images and get different morphologies out of those. This is still not very clear how machine learning can help us with that, but at least there are quite a few attempts on how to approach this. And then now VLASS 1.2, so that's the second half of the first epoch. We have observed 63% of that by June 1st, and we're expecting to complete everything by the end of July successfully, hopefully. And 51% of the quick look images are already delivered out of the 63, of the 51% of the total VLASS 1.2 area. And even while we were observing, there was a LIGO-Virgo merger event on April 12th, and the quick look images actually already provided an observation limit for a counterpart based on the optical, or the closest optical counterpart. So I alluded to that there are some issues that you encounter when you're doing a survey and you look at data closely. One thing is that a lot of surveys actually share in common is ghosts, especially for radio interferometers. That's an issue where here is the source, and then you see a ghost of the same source. And what happens here is that the telescope did not update the phase center according to the, or it falsely updated the phase center according to the metadata. And so there's some confusion about where the correlated phase center was in the data, in the visibilities, and so you generate a false image shifted by a fixed amount of a multiple of the phase center that we shift. And yeah, so we had this quite a bit in VLASS 1.1. We identified the issue by the middle of VLASS 1.1 and got rid of it and flagged the data accordingly so that there are no ghosts in the final data products. But we found some new ones in VLASS 1.2 for a different reason. So we have to keep an eye out for things like this. Another issue that crept in was we have two sets of antennas in the array. The VLA gets slowly upgraded over time. And so some of the antennas have a new antenna control unit. Some of them have an old one. And they were not pointing at the right spot at the right time. So about 20 antennas were pointing slightly different than the other antennas. And then once you try to do spectral indices, you will actually notice that there's an issue. This can be fixed in software, but of course it takes time to write that software. So just in general terms, the survey is meeting the specification in resolution, beam shape, and sensitivity. The area covered, as well as the fraction of quick look images passing the quality assurance. So that's the good news. Currently, we're not meeting the specifications in the time to deliver the quick look images. So we would like to be within 1 week. And currently, we're between 1.5 to 3 weeks, which is still pretty good, but we're working on that, getting that faster. And then we have a little bit of an issue with the position accuracy of sources. Right now limited to the 0.5 to 1 arc seconds, but it should be better. And the spectral index determination is also something that we're working on, which had to do with the telescope pointing slightly offset. And then source polarization is one other area of investigation where we have the beam. Since we're using the entire beam for the mosaic, we have to worry about beam polarization. And we're experimenting right now with how to remove the beam leakage or the beam instrumental polarization leakage in order to get the correct answer for the entire mosaic. And then we are still testing the commensal observing with real fast. So just to give you an impression, so this is the quick look position accuracy that we have basically compared the sources that we found in a test field to Gaia DR2 positions. And we saw that in right ascension, everything is more or less within errors. But in declination, we see a systematic change in the offset between Gaia and VLASS. So this is just to keep in mind when you're using quick look images for your science, these are the limitations that you have to deal with and that we will address once we are releasing the single epoch products. And this is showing for single epoch how we're going to be addressing these is we will be using a different imaging algorithm, which is using A projection and W projection. It's a different gritter algorithm. And unfortunately, that one is about 50 times slower currently than what we are using for the quick look imaging. And but the good thing is that the source positions are improved. And the spectral indices we're looking into right now. But they should be better as well. So you can see that this is just an example of one calibrator that was observed. This is the calibrator position. This is what we get from AW project. And this is what we got from the quick look images. So at least everything is consistent here once we're using the single epoch. And this is the difference you're getting. You can expect in terms of, I mean, you have to look very closely. So this is from the quick look. You get a little bit higher resolution from the single epoch. And because of the W projection, there's a little bit less smearing of the emission that you're observing. So we will be focusing on solving those issues, the remaining issues with the single epoch products that then will come out. And we're working very hard on the polarization part of getting that one right. So since they're more compute intensive, the single epoch products, and we have to use an algorithm that we didn't plan for, we end up with not enough compute resources that we have at our disposal, so we're trying to find more funding to do that, or more partners. And so because of that, everything is going to take a little bit longer. Nevertheless, there's the VLASS defining paper we have just submitted, I think last week, to the Astrophysical Journal. And the survey team, this is just to name all the people involved to give you an idea. So this is within NRAO, the scientists who are involved, and then we have a number of data analysts dealing with the quality assurance. And if you have some ideas, you want to contribute to the Sky survey, a good starting point contact, or if you want to, you don't have to advertise it, you can just use the products and do whatever you want with it. Everything is public. But if you want to contribute to the larger effort, you can contact the board chairs, Chami Chatterjee or Tracy Clark, and they can point you to the right people, because we have sub-working groups for different areas that are working toward a common goal as a team with VLASS data. Just finally, for the VLASS part of the talk, to access the VLASS data, there's something called, if you know how to access the data, the archive data from NRAO, there's archive.nrao.edu. Now there's an archive-new.nrao.edu. This will be also for PI science in the future, but right now this is mainly tested for VLA Sky Survey data. And so you can download all the calibrated data. So you can get the calibration tables from there and the raw visibilities. And you can restore the calibrated data sets. If you want the quick look images, they will be available in the archive in the usual archive interface, but at the moment they're not easily accessible there. So what you can do is you can go to archive-new.nrao.edu/VLASS, and then you get to this directory structure where you find the pilot quick look images, the VLASS 1.1 and VLASS 1.2. And everything is there, the square degrees. And there's an overview in each directory that you can go here to the tile definition. So if you're looking for a particular RA and DEC, you can find out the naming, what you need to look for. If this is too cumbersome for you, the CADC, the Canadian Data Center, they've already ingested the first half epoch of the VLASS Sky Survey into their database, and you can actually search and compare with other surveys within there, and you can have cutouts made from the VLASS data. This is kind of a prototype, but it should be already public or publicly available. And if you have any more information, there's the main web page for the survey. We have a new web page that will be coming online very shortly, and then there's an EPO web page as well with some material. And there's actually also a public wiki page where we collect our memo series for the survey. So I'm gonna, if there are any questions now about the VLA Sky Survey before I go to NGVLA. Yeah.
How did you do the spectral index? Is that an in-band spectral index? Or do you have to use data from the NDS station?
You will get both. You will get an in-band spectral index, which is from the single epoch continuum, which will be generated from that. And then you can also calculate a spectral index from a cube, which has the 16 spectral windows in there. So if your source is bright enough that it shows up in the cube, you can also obtain a spectral index just from the slices in the cube.
Could you repeat a little bit the comparison between the Gaia and the VLA positions? I don't understand. Should we trust in the position derived from VLA or in Gaia?
I would say trust in Gaia. No, so these positions, there's a systematic offset, and we think that it is somewhere in the imaging of the VLA data that is introducing this declination offset. It's not very large. I mean, you see here, this is 0.5 arc seconds, plus minus 0.5 arc seconds. But of course, we can do much better with that data, as you can see here in the RA. errors. So we're trying to figure out what is causing this. If we don't, we will remove this in the final product. But for the quick look, you will be limited in astrometry. Yeah, I'm not discrediting Gaia here. Okay, so I'll move on to the second part of my talk, which is another major initiative that NRAO is currently pushing along, and that's the next generation very large array. And just a little timeline that we're kind of anticipating. I'll show you a more detailed timeline. So in 2016, the project office was established, and it was mainly done with some rededication of some funds that were unused within NRAO. And then in 2020, we're expecting the Astro 2020 report. So the project office's primarily job right now is to write the proposal for the Astro 2020 for the decadal survey. If it is successful, then it will enter into what the National Science Foundation calls the MREFC candidate study. That's the mechanism to get large projects funded through the National Science Foundation. And then if that is successful, basically the goal of this is to have a plan ready, a shovel ready, and then once the funding is secured, construction would begin in 2024 with early science 2028 and the complete construction finished after 10 years. So what is the next generation very large array? So the main, the headline scientific frontier that it should address is the thermal imaging at milli-arc-second resolution. And the goal is to have 10 times the sensitivity and resolution of the Jansky VLA and ALMA. And the frequency range that is anticipated is 1.2 to 116 gigahertz. And the array we would locate in New Mexico around the current VLA. It would replace the VLA, and it would extend its baselines all the way down into Mexico and all the way over into Texas. And then there are a few stations even further out that I will go into. In terms of comparison to the VLA, so this is effective collecting area versus frequency. There's an atmospheric absorption cutoff that we can observe in. Here's the VLA and here's ALMA. Here's SKA1, what is anticipated for SKA1, and then this is what NGVLA would allow us to cover. Not to say that it doesn't really want to compete with SKA. I'll have some other slides on this. So it's supposed to be complementary between SKA, ALMA 2030, and NGVLA. And the key science goals are basically the primary one, and as I mentioned, is it's basically trying to study the formation of terrestrial scale solar systems, and then of course, and then the second one is astrochemistry and evolution of galaxies over cosmic time. It should be able to do pulsar science and the evolution of stellar and supermassive black holes. So it's just a slightly different view. So this is this plot again with the effective collecting area. And here you can see the frequency range and the angular resolution. And you can see here basically this is the line of where the terrestrial zone planet formation at 1 AU could be observed. So the NGVLA would be able to do this with the long baseline option in terms of the resolution. And this is just in comparison. So so you can see nicely that the SKA will go much further down in frequency than the NGVLA, and it will basically bridge the gap between SKA and ALMA and provide much more capability than what the VLA has now. And this is kind of the area where it will be in. So we will have SKA, we will have ALMA, we will have the missions HAB-X, and we have a far infrared surveyor. We have the 30-meter class telescopes, and we have JWST hopefully in orbit. And so with that, together with that, it a great synergy to have a similar capabilities to probe the same targets with the radio. There's a Science Advisory Council, which is the interface between the community and NRAO. It was established in 2016 when the project office started. Here are the members. It's basically, they were leading the science book. They review some of the documents we're generating. It's basically a check for NRAO from the community that we're not getting on some strange track with the design of the telescope. And then there's also some international participation, primarily Canada, Japan, and Germany. And these are all the contributing partners or the institutions so far. So there's already a strong community behind supporting the NGVLA. Very recently, well, I should have put a web link there. But you can go to the NGVLA webpage, ngvla.nrao.edu, and you can find a link to the NGVLA project book. It's all public. We have 80 or more requirements for specifications that we're processing right now based on that and their community studies. The book is about this thick. Unfortunately, I don't have a copy here right now. And that's basically what the science case is behind the project. And that defines the technical requirements. And so for the Astro 2020, there was also a collection of white papers. They were collected. There were 592 submissions to the whole process. 86 of those papers, about 15% of those white papers mentioned the NGVLA project. And this is just in comparison to these other next decade projects, how often they were mentioned. So this was the most mentioned facility to be proposed for the next decade. And this is just to highlight some of. So we have defined, based on all of this work, the key science cases. So the key science case 1 is unveiling the formation of solar system analogs. So this is a simulation. We're trying to actually measure something like this and make movies of planet formation. Then of course spectroscopy. The telescope has to be very good at doing spectroscopy like ALMA, and in order to detect the prebiotic molecules and provide the chemical conditions for the forming of solar systems, and maybe learn something about life in general. Then there's a case number 3, which is charting the assembly and the structure evolution of galaxies. This is measuring the total molecular gas content in galaxies, and is basically bridging or making with more sensitivity the CO line transitions available through the NGVLA. There's also the larger structures that can be then imaged, and that goes into the thermal imaging part. And then the 4th science case is for the pulsars that to look into the galactic center, and in order we're still looking for that pulsar that is really close to Sagittarius A star, in order to see the gravitational effects on that pulsar in relation to the black hole, and so NGVLA would be also pushing in that regime, and that defines the low frequency end of the telescope, of the science requirements. And then the last one is the formation and evolution of black holes in the era of LIGO and other similar experiments. Okay, so coming to the technical baseline. So based on all of these science requirements, we defined the frequency coverage. We defined a main array of 214 times 18 meter antennas, which will have fixed antenna locations. So unlike the VLA, they will not move around. The short baselines will be smaller antennas. Well, we will have 4 18-meter antennas that will be operated in total power mode, and this will fill in the UV hole. And then we have 19 6-meter antennas that will deal with the short spacings. And then there will be an additional long baseline array of 30 18-meter antennas that will be located in the current VLBA on VLBI scales with up to 8,800 kilometers. And this is all part of the baseline design. And these are the frequency bands with the low frequency cutoff here. This is the center frequency and the high end. This is the bandwidth in each band here. And so the widest bandwidth that we have will be 46 gigahertz. And they will be placed in 2 doors. In the interest of time, I'm just going to skip that. That was just a video of showing the different scales. So this is the main array. The main array will be situated where the VLA is now. It's anticipated to be in this kind of spiral configuration. And this is the core of the array. So this is kind of a pseudo-random configuration. And then going out to a few 100-kilometer baselines, it will be going out like this. And this is already defined through available fiber optics cables. And you can see that here, the red lines will be fiber optics operated by the NGVLA, and then the further out stations are most likely going to be running on commercial fiber optics. And then, so this is just showing you the short baseline array. So this is what will be in the core, just this little cluster inside the core. And then we have the long baseline array, which is going all the way out to VLBI baselines. Right now, the VLBA stations, we have current telescopes here and here. And then there's one up here. Those are existing ones, and there's one here. And then we're going to add another site here. And then there's another one in Arecibo that we would add antennas, and then another one up here to double up and create more shorter baselines on the long baseline. This is mainly for calibration purposes. The antenna concept itself looks pretty familiar to SKA. It's mainly, the main idea using the feed arm low is that for maintenance purposes, so that you can tilt the telescope down, you can drive up with the truck, you can do maintenance on it. There's a question about life cycle cost. We're trying to do this very low maintenance, so these antennas should not be visited, or they would be visited for maintenance purposes maybe every 3 years. So they have to be self-reliant for the rest of the time. And they have to be, well, we try to be cheap. And so we have 2 designs. One is from General Dynamics, one is from the Canadians, which is a composite, and this is a traditional design. And so the key specs are 18-meter aperture. We have a shaped optics, a surface to 160 micron. And the current schedule that we have defined is we would like to have a prototype ready at the VLA site by 2023 before we start the construction. But the prototype ready design is supposed to be ready by 2021. This is the receiver concept. So we have 6 bands in 2 cryogenic doors. So there are 2 boxes that basically will be attached on a linear drive system, so we can just index them linearly. And then, although that's not defined yet, maybe we might have to add rotation to it. But at the moment, we want to do it linearly, and these are the specifications for those. Software and computing considerations. The goal is to have science-ready data products. So both for the first observation the telescope takes to the archival projects, the goal is to have already provide science-ready data products. The good thing is that we think that our analysis shows that we are able to actually save the raw visibilities from the telescope, and these are the data rates that we're expecting. We're designing for a peak data rate of 128 gigabit per second and the average of 25. And so a 4-hour observation would produce 372 terabytes and require about 1,000 cores to process in a few days. And so the computing will be challenging, especially for the lower frequencies where you have a wider field of view that you need to worry about. But we think we can meet the needs with the off-the-shelf clusters. And then, of course, there are some parameters that define whether we can deal with it or not. That's the numbers that you're probably interested in. It's like, how much is all this going to cost? So our estimate is $1.9 billion in 2018 base year dollars. So if you add some risk, then you have 2.3 billion. And we are seeking about 25% international partners, and we're in discussion with those. And they seem to be very keen on participating. So we're talking about a 1.4 billion US commitment to this project. And also in terms of the operations budget, we have a cap of 3 times the current VLA plus VLBA operations budget, since it will be replacing those telescopes, and that's capped at currently $80 million a year for 2018. And so this makes it very critical to keep the maintenance costs down. And even if it means it costs a little bit more to build, this is the hard part to come up with. It's always difficult to run a facility in terms of finding the funding for it than to build one. So everything will be reviewed, the entire costing and the whole plan that we have outlined by the Astro 2020 process, and then in a couple of years we will know whether this will move along or not. This is kind of the rough timeline that we have set for ourselves. So there are two timelines here. This is the Decadal Survey 2020 roadmap. This is the construction roadmap. I don't want to go into the details here. In terms of technical risk, I think there are basically 2 major or 3 major risks. One is we need to still rely on operation costs to go down for computing. We are really concerned about the RFI environment. There are low Earth orbit satellite revolution is just starting. And this is a projection here from The Economist. There are these satellite constellations of small, large constellation satellites, and they're going to put thousands of satellites in orbit. And they have already started putting a few hundred in orbit. And they will put a spot beam on the telescope at any time. And they will use higher frequencies. So this is a big concern on how we're going to deal with this. There's no clear answer yet, and in terms of regulation, we're weak against the industry. And then there's some other cost versus risk curve choices that we have to make in terms of receivers. But I think we understand the technology really well. Maybe the antennas are a little bit of a risk at the moment, but most of it is pretty well understood. There's a science meeting going to happen end of June in Charlottesville, Virginia. And it's particularly highlighting the participation of early career astronomers, and because those will be the next users of this facility. And that's the end of my talk.
So that's some of the questions.
This instrument will have a large frequency coverage. What are the plans for a receiver installation? Will you start with the highest frequencies or the lowest frequencies or something in between?
Be installed at once. I don't think there will be a staging. Maybe there will be a staging between the lowest frequency, but all the upper frequencies, so there's in the band table that I showed, or here you can see there are two Dewar boxes, and you could separate the lowest frequency, the 1.2 gigahertz to 3.5 gigahertz. You can ignore that. I mean, you can say we're going to install that later, and we're going to focus on the higher frequency ones first. So that is a possibility, but it has to be what we call the line replaceable unit. The line replaceable unit would be that box with all the Dewars. I mean, you can stage it, but I think the current plan is not to stage it.
Regarding the simulation of the protoplanetary disk with some embryos, could you say again the setup? I mean the frequency, the sensitivity, and the angular resolution to see these features?
Yes, this simulation was for 100 gigahertz. I don't know what sensitivity it was meant for.
It's about 3 million.
The highest frequency, that I suppose the...
5 AUs. It's a Jupiter analog orbiting at 5 AU.
I don't know, in the angular resolution.
I don't remember what the angular resolution was for this.
You have the reference.
It's the reference here is Luca Ricci made this.
Ah, okay.
Yeah.
Is there going to be a new generation CASA?
Well, of course, CASA will be continue to be developed, but I presume that I would say the lessons learned from commissioning the next the Jansky VLA, going from the old VLA to the Jansky VLA, having a mature software package that we understand is actually very important. You don't want to develop your software while you're commissioning the hardware. So you need to have some package that you can rely on. So if we can get CASA now to where APES is, or APES was at the time of the VLA commissioning, then we can, now well, ALMA was commissioned with CASA and it was a very hard lesson. And so I would say the current CASA will be relevant for the NGVLA, yes. And of course the data formats and all those has to be made compatible and to deal with all those data, these large volumes. And there's a project going on thinking about exactly this. What do we need to change in CASA in order to make this happen? And there's another initiative currently happening at NRAO, which is called Science Ready Data Products. And this is Science Ready Data Products for the VLA, kind of similar to what ALMA is producing. And this will be leading, or will be kind of the prototype of how we want to design this for the NGVLA.
So the design looked like there were single pixel receivers rather than phased array feeds. So does that mean that most of the science cases will focus on targeted observations rather than wide surveys? Yeah.
Focused on targeted observations. Although you have 18-meter dishes, I mean, you will still be limited to whatever the 18-meter dish can see. But yeah, there's no plan at the moment for multi-pixel receivers. It's a weight issue on those arms. You cannot add more to it. I mean, it's hard to, you have to replace it with something else if you wanted to go that way later. So yeah, I think this is more meant of what the VLA is now. You have separate survey telescopes, and then you do the point and shoot with that telescope.
Okay, thank you. Just one thing, the local contact of Frank is Ivan Agudo. If you want to ask more questions to Frank, please contact Ivan. And thank you again, the speaker.